Okay, good morning. Today we will cover Chapter 7, Failure Criterion, and that's the main topic we're going to cover. Well, there could be some other issue like stress concentration and fatigue and creep, but a most important point of material failure is about the failure criterion. So it's important to understand what is all about the failure criterion. I'd like to get back to at that flow chart, 8+1, and this one. And again, we went through all the procedures. We defined a strain in last week, and we defined the stresses, and we also studied about the stress transformations and strain transformation, and the strain is in terms of a displacement, and stress has to meet the equilibrium condition. So now, last week we studied about the stiffness, which relate three-dimensional stresses and strains. Now, most important point here in design, for example, where we want to design certain structures like a component in automobile and aerospace structures, and we, for example, let's say we have a wing and airplane wing, and we have lots of load applied to there, and this will bend, it will deform like that. And so let's say we want to design of this wing and design this thickness, for example, how thick we have to make this skin of the wing of the airplane. Well, here we have forces, certain forces. So we need to specify the materials, of course, material properties, and we have to specify deformation condition. Well, since this wing is attached to a fuselage like that, and let's try to fix this one to consider attachment to main structures. So that is the deformation condition. Now the point is that when we can calculate the stress here. Say I will draw a three-dimensional. We have all kinds of stresses and each surface, and here and there, and all 6 components of stresses. And there will be a deformation and strain and things, but the topic we're gonna cover is the strengths, meaning that let's say we have a stresses, and we need to know this material will be safe under these stresses. Well, if this stresses over the strengths, then it may fail. The wing will break, which we don't want to happen. So this stress basically, let's say, indicate this is the strength, yield strength. Okay, yield strength will be less than, should be less than yield strength, right? The yield strength is simply we measure from uni-axial stresses like a simple coupon, and we apply the stress, and there will be some kind of yield or failure, and this is called sigma yield. And now it's important to consider this failure, but this failure occurs when this stress is uni-axial. Uni-axial means only one directional load. Now, question is that we have a three-dimensional stress state, so six components of the stresses. Now, how can we make a judgment that these stresses will be low enough not to cause any material failure when the material strength is the sigma y, sigma yield strength. But again, this yield strength is measured under one-dimensional stress state, but we have a six-component, three-dimensional stresses. So we need to have some function of this sigma ij, and it should be less than this yield strength, which we measured using uni-axial load. So this is called, we call failure, okay, failure criterion. Failure criterion, and that is the very important procedures. Very important procedures in design. So for example, this wing skin is too thin that this stress state will be above this strength, it will fail. And if this one is too thick, too thick, well, certainly this will be less, but we don't want too much less, we don't want to use too much materials. So we need to know what when the failure occurs under this three-dimensional stress state. That's the purpose of our study, and this studying of this strengths and studying of this one, this is a step called failure criterion. Okay, this is a failure criterion, and this is a subject we want to study right now. Okay, let's get back to that chapters. Okay, so chapter 7. Now, as I mentioned, this is the same point as I mentioned using that A+1 flow chart. The maximum allowable stress which materials can sustain without failure are limited by the material strength. We can say like that. Stress has to be less than strength. Where for one-dimensional case, it's clear under simple uni-axial load, where we apply the load P and the cross-section A, then P over A is the stress and strain, and it simply has to be less than yield strength, and otherwise the material will start to yield. Yield means plastic zone, which we don't want to happen. And so in this case, let's say given, well, usually the first P is a given, and now as a designer, we want to design these cross sections not to exceed these strengths, but not to, we don't want to have too much cross section. So designer choose the right cross section of the area or limit externally applied load so that stress should be less than the strength. Now, this is very clear and for one-dimensional cases. But as I mentioned, the point is that multi-axial stresses, in other words, let's say we have a three-dimensional general structures, and we have some boundary condition, and we subject to all kinds of external load. And these structures will have stress and strain distribution. And let's take a look at this point, and where we have all 6 components of stress, sigma xx and sigma yy and sigma zz and also sigma xy, this pair. We don't look at the negative sign, okay? We have to have a sigma xx, sigma yy, but for just a simplicity, we don't show that, okay? And so this is sigma xy, and this is sigma yz, and this is the sigma xz, okay? So basically 6 components. Okay, now again the question is that this material will fail or not, and the strength we have is only sigma yield strength. So so we need to have a function or guideline, or you can say theory, and more precisely we call them as the failure criteria. And there are very well-known 2 failure criteria which has been widely used to predict material failure. So one is the Mises Yield Criterion, the most important criterion in failure predictions. So in other words, is called maximum distortion energy criterion. Why we call it maximum distortion energy criterion? Well, there is a reason for that, but at this point, we just focus on how to use this Mises criterion. Second one is the Tresca yield criterion. But in Tresca yield criterion, I mean, it is called, another name is the maximum shear stress criterion. So this is the kind of distortion energy, and this is the shear stress criterion. Well, this a contour, as contour happened to be a very long, slender cylinder, but let's say we have sigma 1 and sigma 2 and sigma 3, and this is just schematic drawing. Say stress inside this envelope, then material will be safe. But in outside of this one, the material will fail, and inside is safe. So this kind of surface is good to visualize visualize what stresses will cause the failure. But anyhow, let's say we study the first topic, Mises Yield Criterion, and the approach is relatively simple. Well, it is experimental observation. Okay, the criterion is not obtained through analytical procedure. It is a experimental observation, so it is nothing but a theory. But that theory works well for many different material, for many different stress states. That's so again is experimentally observed that a function, okay, a function which we will define, in terms of principal stresses, F reaches a constant value when failure occurs. What does it mean? Well, we have a 6 component of a stress, sigma ij, and we can always calculate the principal stress, sigma 1 and sigma 2 and sigma 3. Well, we studied how to calculate the sigma 1 and sigma 2 in two-dimensional case using Mohs circle, but we can extend that procedure to calculate the principal stress in three-dimensional. So this experimental observation says there is a certain function which is a function of a sigma 1, 2, 3, reaches a constant value. Constant value reaches a constant value when failure occurs. Well, then what kind of function is this? Well, in three-dimensional stress state, this function is given or found as sigma 1 minus sigma 2 and square, and sigma 2 minus sigma 3 square, plus sigma 3 minus sigma 1 square. Well, pretty much not that difficult complex equation. As you can see here, sigma difference, the difference of each component and square of each component and summations, and reaches the constant when material fails. Again, this one is experimentally observed, and we cannot say why. Again, is experimental observation. But the main point here is that what is this constant? It says it reaches the constant value when it fails, but the point is that what is a constant value? Okay, it says the this F will reach a constant value when material failure. But what we know is that stress, you know, the strain curve, and here this is the sigma yield, and what it means is that sigma 1 reaches the sigma yield, and sigma 2 and sigma 3 is simply equal 0, right? We know this stress state, and we reaches material. We have a material failure. So let's put this equation into here, and simply sigma 1 equals sigma yield strength and 0 and 0, 0 plus 0, and okay, there is another sigma 1 here, and the sigma 1 here, and the sigma here. Now this value is simply twice of a sigma yield square. Well, so we can conclude that this constant is nothing but twice of a sigma yield strength square of this sigma yield. Why? Well, it says the material will, when material fail, this F reaches a constant value. So the even under 1D, one-dimensional material failure, this F function should also reach its constant value. So we obtain this constant value, and then we on the right hand side to make yield strength alone, we divide by the 2. Okay, now we put this thing into back here. Okay, to back here, and so the and then we divide by 2, Okay, we divide by 2, and we have a root of this, and on the right hand side will be sigma yield. So simply from this observation, what we reach it is this stress will be yield strength when material fail. Okay, so this is a general stress state, and this value should be less than sigma yield, and this one we call yield equivalent stress, or we call von Mises stress. Very important stress in design. So in other words, let's say you have a 6 component of a stress. You get the 3 principal stresses, and then from this you get the sigma equivalent or von Mises stresses. And again, now you have a single number, and this has to be yield strength. Okay, we had difficulties when we compare all these 3 components of a 6 compare with the sigma yield. That was not easy, but now we have a von Mises stress and one single number, and can be compared with the yield strength. Okay, in 2-dimensional case, this is a 2-dimensional. So instead of a 6 component, we have a sigma xx, sigma yy, and sigma xy. Only 3 components, and now we get a 2 component, sigma 1 and sigma 2, and now these principal stresses, we get the sigma equivalent, and this has less than sigma yield. So this is a 3D, and this is the 2D. Okay, but again, the procedure is exactly the same. Okay, so von Mises, let's say this is the 3D, all 3-dimensional stress. Now in 2D, as just mentioned, the sigma 3 will be 0. So let's disregard this sigma 3, and so this term will be simply, we put the 0 here, and the right hand side, and twice of sigma yield strength. And then we little bit of a manipulation, and this equation becomes like that. Well, you can sigma 1 square minus twice of sigma 2 plus sigma 2 square, and plus this is the sigma 2 square plus sigma 1 square, and so this one is simply twice of sigma 1 square because of this and that, and minus there was a twice, and sigma 1, sigma 2 plus sigma 2 square, and sigma 2 and sigma 2, and less than twice of sigma yield. So you will reach these equations. So this is a 2-dimensional version of the von Mises, and if we plot them, sigma 1 and sigma 2, and we can simply this is the this kind of parabolic curve, and here has to be sigma yield, and here is a sigma yield, and minus a sigma yield, and minus a sigma yield, and actually this line, what does it mean? This means that this line means that sigma 2 equals 0, right? And this shows the simply one-dimensional yield strength, one-dimensional stress. And the same for here. Along this line, what does it mean? Sigma equals 0, and this is a one-dimensional. This is the tension, and this is the compression. And compression tension reaches the same strength, yield strength, and same for here. Okay. So this is it. This is the von Mises yield criterion. Now, how about this Tresca? Well, the Tresca now instead of that f function, now this is also an experimental observation. Okay, Tresca yield criterion is also experimental observation, and it says the maximum shear stress reaches a constant value when failure occurs. Okay, so this one you can remember that sigma 1 and sigma 2 and sigma 3 reaches a constant value, and sigma 3 and reaches constant value. Now this F, you can think of the maximum shear stress, and this reaches the constant. What is the maximum shear stress? Well, if we consider in two-dimensional, this is a sigma 1 and sigma 2, and if we plot them in Mohr circle, what do you see? Well, in general, we can have a shear stress, and we have simply x and simply y. X is the what? Sigma xx, sigma xy, and this is a y, and sigma yy, sigma xy. For sigma xy is a positive, and we just connect these two points and then make a circle with this line as a diameter. And now this one is what we call sigma 1 principal. This is a sigma 2 principal. And what is the maximum shear stress? Well, as you know, this diameter radius, this much is the r. R is a simply sigma 1 minus sigma 2 divided by 2, right? That is the basically the maximum shear stress. Okay, so this one, as you can see that this is the 1-2 plane, and this 2-3, we can consider this one as the 3D. Then we would consider this and that, and this one, that, another stress component, right? And so in that plane, we also can have the maximum shear stress, the same as in XY plane. Okay, I will call XY plane. This will call XZ plane. And so you can see that sigma 1 minus 2, and this is sigma 2 minus 3. So we need to calculate the principal stresses. Okay. This one, now sigma 1 minus sigma 3 space that we can have this another the maximum shear stress. So the sigma 3 minus sigma 1 will be the another maximum shear stress. So we can have 3 maximum shear stress for each plane, and maximum of these three will be the maximum of shear stress. So this one is the simply definition of a maximum shear stress, and this maximum of maximum will cause material failure, and this maximum of the maximum shear stress will reach a constant value when material fails. Okay, that's the key observations. Now, again, similar to von Mises, and how do we determine this stress? I mean, constant value. Again, what we know is that simple stress strain curve, and here we have a tension. I mean, the one-dimensional curve, and it reaches the sigma yield. Again, sigma 1 equals 0. I mean, sorry, sigma 1 will reach sigma yield, and sigma 2 equals 0, and sigma 3 equals 0 when material fail. Okay, so let's put these things into here. So sigma 1 will be a sigma yield, and this one 0, 0, 0, 0, and this one is a sigma yield. Okay, so this one will be a sigma yield, and this one will sigma yield, and constant. Okay, so what is a constant? Well, this, as you can see here, this constant will be simply sigma yield divided by the 2. Actually, we should say sigma yield divided by 2. So that is the this one. Now, so this is the basically the von Mises criterion. I mean, Tresca yield criteria. Okay. So let me put this back to here, and simply we say, oh, this will be 2 divided by yield, which will determine from one-dimensional stress state. Well, we can just eliminate all 2. So this is the equations. This is the yield criterion, Tresca yield criterion. Okay, now for the two-dimensional case, two-dimensional where sigma 3 equals 0, and so the when sigma 3 equals 0, we have a this term, and remember this, we had a sigma 3 and sigma 3 minus 1, so we don't have that one. And this was the 2 yield over 2, so we divide by 2, and this one is the two-dimensional yield criterion. Okay, so we can plot them. We can plot them in a two-dimensional case, because I will put this one equal sigma yield. Okay. So we can plot them in sigma 1 and sigma 2, and these equations gives us the line like that, and like that, and like that. Okay, this we have where we have an absolute, and you need to check all region. And here we have a sigma 1 bigger than sigma 2 and bigger than 0. And here we have a sigma 2 bigger than sigma 1 and positive. So in this area, what do we have? What will be the maximum? Well, maximum will be, the difference will be less than this one. So this will be sigma 1. So in this region, sigma 1 will be sigma yield. That's the simple equations. and that's why we have this vertical line. And this one is similar. We have this. Now, how about here? Here we have a sigma 1 is a positive zone, and sigma 2 is the negative zone, right? This zone. And in this this condition, take a look at that. What will be the maximum? Well, maximum is simply this one because they are different sign. The difference will be bigger than each value. So in this one, we can say sigma 1 minus sigma 2 equals sigma yield. And as you can see here, sigma 1 bigger, positive, and sigma 2 is the negative, right? And sigma 1 minus sigma 2 will be okay, this graph will be like that, right? This graph will be like that, and similar we can draw. Okay, that is the two-dimensional failure envelope for Tresca. And we can compare Van Mises and Tresca in 2D, and you can see that we have a common point here, here, and here, and there, and others, there are a little bit of a difference. Again, this one is the sigma 1 square, 1, 2, plus sigma 2 square, and equals sigma yield. And this blue one is from here. And experimental data shows that, you know, all the data is very near to here, and sometimes between those two criteria. And so the it's okay to use either one, but if you want to be more conservative, you better use the Tresca. Tresca is safer and safer than Van Mises. But Van Mises is a more common value and very easy to use since we have only one single equations, which is okay. I forgot to put it here. I mean the divide by half. No, we need to root 2, right? Okay, so oh no, just root 2. We'll get back to this equation, and here, as you can see here, root is just a root. Okay, that's all about the Tresca and Van Mises yield criterion. Okay, and let's try to open this stress transformation Excel file. I hope you remember that these all stress transformations, right? And this one, I will just add just add a failure criterion. And as you can see here, the main point is the sigma 1 and sigma 2, principal. And here is the, since we have a sigma and principal, and three component. I mean, third component is simply 0 because we consider only a two-dimensional case, right? So we can say that this principal 3 is equal 0. So the try to delete. Okay. Now, so let's say von Mises. I'm trying to. Okay, von Mises. And what will be the equations? Let's get back to von Mises, and simply this is the equations. Okay, this is the simply equations. This is the equation we need to have. So whenever you say these three principal stresses, then the square equal square root and the sigma 1, okay, principal component 1 and minus and 2 and parenthesis and 2 plus sigma 2 minus sigma 3 and square plus and sigma 3 minus sigma 1 and square and square root. Okay, so that is the von Mises stress. Okay, simply we didn't pay much attention here. We don't consider unit, but whatever can be unit can be Pascal, or unit can be megapascal, and whatever value for given this one and the simply this is the von Mises stress state. It's not right. Oh, we didn't divide by half. Okay, sorry, we didn't. We should divide by half, and so we have to divide by half. 1 divided by half. Okay, and parenthesis, and we can have a parenthesis. Okay, so please look at again. I will click this, and square root half times sigma 1 minus 2 square 2 minus 3 square 3 minus 1 square, and that's the value. Now, trying to show you that, you know, since the 1, 0, 0 were only uni-axial, then you have to see that of course the von Mises stress will just equal 1, right? You can see that 1, 0, 0, 0, 0, 1 and divide by half will be 1. So you can see the physical meaning that it has the something representing stress state. Say it is a 2, of course it's a 2, but main point is that what if we have a 1 and 1? It's the same 1. But what if we have a 1, 1, 1? Ah, it's a 2. See, this one is very much, I mean, we cannot easily guess, but this number is represent these three stress states, and this one should be less than yield strength. I would call sigma yield as whatever, say just 1, okay? It can be arbitrary number. And as you can see here, if it is 1, then von Mises stress will be simply, it will cause the material failure, okay? Now, let's consider Tresca. Tresca, let's get back to here. And Tresca, we have a this one, okay? We have this. Tresca, well, we don't have quite final equation here. We simply we have to say this one, okay? This one we can divide by 2. I mean we can multiply 2 and 2 can disappear. So this will be a formula, right? So on the left-hand side is the, we can call Tresca stress, okay, Tresca stress, and get back to here. And Tresca, so the equal maximum of, and the absolute value of the sigma 1 minus sigma 2 and comma and absolute value of, well, 2 minus 3 and parenthesis and comma and absolute value of 3 minus 1 and parenthesis, and then okay, that is the value, Tresca, and this value has to be less than von Mises, okay? And here we didn't okay, so you can imagine what kind of von Mises or Tresca you will have. You can enter the any value and you can see this value. See here, they are a little different. Of course, 1, 0, 0, we should have a 1, 1, right? That's the material failure. And this value should be less than yield strength, clear. But what if we have a 2 and 1 all together? Ooh, von Mises stress will be a 1.7 and Tresca will be 2. And it's not easy to just predict, but we have to go through all these equations to get this value. Again, this, for example, I will try this one as the 1.5, and this one I will try 0.7, and okay, I will do a little bit different value. What I'm trying to do is that 0.6 something. I mean, some value. Oops. Some value. Now, say sigma, I will draw for our visualizations, and okay, we have, say we have stress state and something like that, what does it mean? We have a sigma 1, sigma xx equal 1, 1, okay? And sigma yy is a little bit less. Sigma yy equal 0.5 and 0.5. Now, the sigma yield equal 1. Question is that, will this material fail or not? Well, if we look at the Mises, this stress state give us the value 0.9. So this is a less than 1, so no failure. But Tresca said 1.1, so it's bigger than 1, so this material will fail. Okay, so again, depends on the materials, the theory, and sometimes it says okay, sometimes the other one says not okay. That is simply because of these pictures. And if we go there, Excel and show here, and simply the 1.1, where is this point? 1.1. 1.1 is the, say this is equal 1, okay? This is equal 1. And 1.1 is somewhere here, okay? And 0.5 is somewhere here, right? Here. So this will be 1.1 and 0.5. So as you can see that, oh, well, the Mises says is inside of envelope, that's why it's less than 1. So, well, it's okay, safe. But Tresca theory says, well, this point stress is outside of this region, so its value is 1.1 bigger than 1. So, oh, it's not okay. So depending on the theory, one theory says okay, the other one says not okay. So as you can see here, sometimes there is some little contradiction. So we need to be careful at this point. We better use, well, but it's up to a designer which one you need to use. But again, the most important is that to use the formula and for these different categories. Well, it took 1 hour to go through, but the final equation is relatively easy. All you need to remember is that these final equations, okay, not this one, this one, and also this one, okay. I will okay, I will just 1 second. I need to finalize the equations. I better do that. Otherwise, it's a little bit confusing. Huh? So I will have that one and put it here. So final equation will be like that, and we don't need to have just this and that and delete, right? And also here and then delete and 3 minus 1 and here and delete. Now this has to be less than sigma yield, this one. Okay, so this is the final equations, and from Mises. And I would like to summarize new slide here. And this one, you can say this here and here and this here. Okay, pay attention. This on the right hand side, you have a material yield strength, and so I will call this one is the Mises, okay, Mises stress. And I will call this one as the Tresca stress. Okay, so all you need to do is just get the Mises or Tresca, and each stress has to be less than yield strength. Okay, wonderful. Now this one, I would say this is the a 3D, three-dimensional, right? 3D case, three-dimensional case. And but how about this 2D? 2D is where we sigma 3 equals 0. And simply all you need to do is just put these things into a 0. And 0 means this one is a 0. And that is a 0. And you can simplify a little bit. And what do you have? You have a sigma 1. Yeah, I mean the sigma 1. And okay, I better do this way. I will. Okay, 1 and 2. Okay. Oh, we already have this equation, I think. We have somewhere in 2D, right? This one. Okay. And 2D, we have. Yeah, we need to have a square root. Square root, and we have to have these terms inside, and disappear. I mean this one delete. Okay. So this is the two-dimensional term for the what? Mises. Yes, Mises. And so the nothing special is we put the 0. Okay, for 2D, we put into a 0 here and 0 here. Okay, don't forget we need to consider I mean sigma 3 equals 0 here. Okay, this is the I call a summary of the theory. Okay. Mises versus Tresca criterion and 2D and 3D and 2D. Okay, good job. Okay, so this is what I would like to cover today, and then please keep these equations in mind and then try to remember this. You have to remember this equation. Well, you don't need to remember 2D, but 3D basically easy to remember, right? Okay, so see you tomorrow. Bye.